we're trying to derive the equation that describes the angular frequency of a pendulum. And to do that, we're going to relate it back to the equation that describes the angular frequency of a mass oscillating on the end of a spring. Now recall, for motion to be simple harmonic motion, the restoring force, F, well, I'm going to call it FR, has to be directly proportional to the distance the object is from its equilibrium position and some other constant. Now for a spring, this other constant is the restoring, or the spring constant, K. And if this is true, we have simple harmonic motion. So we have the restoring force in a spring is equal to the spring constant times the distance x that it's pulled. And if this is true, then we know the angular frequency is given by the square root of K, the spring constant, divided by m, the mass that's actually oscillating on the end of the spring. So if we can find an analogous equation for a pendulum and see that it's undergoing simple harmonic motion, then we should be able to make the appropriate substitution to find the angular motion, or the angular frequency for a pendulum. Now, we know there's no spring constant in a pendulum because there's not a spring supplying the restoring force. It's gravity. So if we take a look at this, we have our pendulum pulled some angle theta from the equilibrium position. And since theta is measuring our amplitude, what we're hoping for is some equation that has F equal to some constant K times the angle it's pulled, or the amplitude. So we're looking for something like that. Well, in a pendulum, the restoring force is supplied by gravity. Gravity is pulling straight down, so I have mg pulling here. Now there's actually tension in the string which pulls this way, Ft, and it's the difference between these two forces that causes the restoring force. And we can see that difference if we draw this out in its components. So one component of gravity acts against the string, and another component of gravity pulls it back towards its equilibrium position. So this is my restoring force, Fr. And since this angle's theta, because of this angle's theta, what we have is the restoring force is equal to mg times the sine of the angle. Now this is a little bit sad because we were hoping for some constant, which we have, mg, times the angle theta, but we don't have the angle theta, we have sine theta. However, we're not out of luck yet, because it turns out sine theta and theta actually are almost the same for small angles. So here I have a graph of y equals sine x, which is given by the red line, and y equals x, which is given by the blue line. And my x scale down here is in radians, and you can see that by the time we get up to about 0.4 radians, they start to diverge a little bit, but these two graphs are almost identical for the first 0.4 radians. And 0.4 radians is actually kind of a lot of a circle, right? There's 2 pi radians in a whole circle, so pi radians, or 3.14 radians, gets me half a circle. Pi over 2, or about 1.5 radians, gets me a quarter circle. Pi over 4, so now we're about 0.75, gets me about 45 degrees. So a half a radian actually is a respectable amount of the circle. So this actually still has a pretty good angle that it can oscillate through. So what we can do is we can say, well, as long as our angle is small, we can replace sine theta with theta. So sine theta is approximately equal to theta for theta less than, much less than 1 radian. So I'm going to do that. I'm going to say, okay, so that means my restoring force is about mg theta. So now I do have this fancy equation. It does meet this term. So I can assume simple harmonic motion for small angles. For large angles, this relationship breaks down. Now we want to come back to this equation. Can we figure out what this should be? Well, this equation had the x in it, which is a distance, but we had this theta in it, which is an angle. So we should be able to do something. If we can get theta in terms of some other parts of this pendulum, then we should be able to come up with a simple relationship here. So let me erase that, and let's see what we got. Now the pendulum is actually swung through a distance, this arc length, x. Now remember, as long as we're measuring in radians, then what we have is theta is the ratio of the arc length x to the length, or the radius, in this case L, which means I can replace theta with x over L. So what I really have is the restoring force is equal to mg times the arc length x divided by the distance L, which is handy because now this becomes my K up in that equation. So Fr is equal to mg over L times x. And I'm going to use that K in this equation. So my omega, or my angular frequency, is given by the square root of K over m. Well, this becomes mg over L times 1 over m, square root all that, and what I get is the square root of g over L. So what this shows me is a pendulum has a similar equation to that of an oscillating spring. And in fact, it even kind of makes a little bit of sense if we look at this in terms of the physical quantities. Up here, the spring was supplying the restoring force, so the angular frequency responds according to that. Well, on a pendulum, it's gravity supplying the restoring force, so we have g. On a spring, it's the mass of the thing on the end, that's inertia, that is opposing the restoring force, or opposing that acceleration, so we have m in this equation. On a pendulum, we actually have something that's swinging in sort of circular motion or rotational motion. And remember, it's the moment of inertia I that opposes rotational motion. And so down here, and I is actually proportional to mass and the length squared. And so it makes sense that the longer the pendulum is, the slower it's going to swing because it has a greater moment of inertia. And so this final equation, omega is equal to the square root of g over L, actually does make sense in terms of its physical quantities, and especially when we compare it to that of the spring.